Yeah, so today we have Itamar Mor from Queen Mary University of London, who is going to talk to us about profinite Galois and NK-H local homotopy theory. Thank you.
So thanks for inviting me. And apologies for the delayed start. So yeah, my talk's going to be about profinite Galois descent and local homotopy theory. And broadly, so what might your aim be? Okay, I don't think I can get rid of this. Okay, so broadly, so one aim one might have is to compute some interesting invariants of the KH local category. So the KH local category is, in some sense, one of the kind of smallest irreducible chunks that you can, into which you can break the stable homotopy category. So for example, you might want to compute this group H, which by definition is the group of invertible objects X in the KH local category up to equivalence. Or you might kind of categorify that problem in a sense, and ask about the Brauer group. So this is Azumaya algebras in the KH local category up to Morita equivalence. I think Azumaya amounts to saying that modules over A is an invertible module over the over SPKH. Or you might be interested in computing some strict units. So the KH local sphere is an infinity ring spectrum, and so it has a spectrum of units. I guess a spectrum of units. GL1. And GL1 is quite easy to compute. But if you want to try and work out which of those units are strict, so which maps from the sphere into GL1 factor through Z, then that's a much more difficult. And so generally for these computations, the strategy, which goes back to Morava, is to pretend that the KH local category is something like, well, we take the category of the infinite category of KH local modules over Morava E theory, and we form some kind of homotopy fixed points for an action that's defined on Morava E theory, and because it's defined on Morava E theory, we can kind of base extend along that action. And so if we have nice invariants F, so for example, if our invariant preserves all homotopy limits, then we might hope to be able to compute the value of the invariant on the KH local category as the homotopy fixed points for the value on the category of Morava E theory, on the of E modules. And because Morava E theory is much simpler than the sphere, that can kind of simplify the computations a little. So if you need a little refresher, here's a cartoon. So the idea here is we use this dictionary between the moduli stack of formal groups and the category of local spectra, given by the Landweber exact functor theorem. And this is a picture of the stack. And it's got all these infinitely many points, but they split into strata, and we can just look at an open stratum like this. And on the stacky side, we can restrict sheaves, and the functor in homotopy theory that does that is this LH localization, and kind of Morava E theory is constructed so as to implement that. And then we can further just complete along this section, just looking at one of these points at type H. And Morava K theory is, again, kind of constructed so as to implement that procedure in homotopy theory. And this group G that appeared on the previous point, on the previous page, so that's the automorphisms of this point. So this is a staff, this thing on the left-hand side, and so this point has some automorphisms, and those automorphisms are the group GH. So the automorphisms of a formal group law at type H, maybe well, extended by automorphisms of the field over which it's defined. So Morava kind of had this picture in mind and cooked up these gadgets called Morava modules. So these are GH semilinear modules over the coefficients of Morava E theory. So these are pi star E modules, which have a GH action on the underlying set, which intertwines the action on the homotopy groups of E. So some examples are, well, the coefficients of Morava E theory, or if you have any space or spectrum, you can define this gadget, the completed E homology. And by definition, it's kind of like taking the E homology of X, except that we also KH localize it before passing thumb. And then one formulation of Morava's change of rings theorem is that if we look at this commutative ring spectrum, we can form its atom spectral sequence. And we're going to do that using this KH local smash product. So that's right. So this whole construction you might denote by EH tensor with a little hat. And we're going to form the cobar complex for that tensor product. And that gives us a spectral sequence, and Morava showed that the E2 page of this spectral sequence is given by continuous group cohomology of G with coefficients in the homotopy groups of E. So that's one way in which this kind of heuristic was used to give kind of meaningful computational results. So today what I want to do is kind of make slightly more concrete sense of a statement such as this. And then I want to use this to compute. And I'm going to take advantage of the fact that we're online now, at last, and use my iPad to show you lots of pictures of spectral sequences that would be more tricky on a blackboard. And basically, I mean, we understand homotopy points for group actions quite well. And the basic issue in making sense of this statement that I highlighted a second ago is that this Morava stabilizer group is profinite. And we're kind of okay with homotopy theory of profinite group actions as long as they're acting in a discrete way. So, and it turns out that the action of GH on EH is not discrete. So just as a reminder, so this is discrete in the sense of kind of modules. So like, I don't know, maybe one way to say it is that the stabilizers of everything is or open. And it's not hard to see that Morava E theory fails this. So you can look at height 1, in which case the Morava stabilizer group is ZP cross, the p-adic unit. And they act on Morava E theory, which is completed K theory by Adams operations. And so the action on pi 2 is left multiplication, and in particular, it's free. So the stabilizers are certainly not open. But an exercise is to check that this thing is this, so it is discrete up to P completion. So if you look at the filtered colimit of all the homotopy invariants for open subgroups, and you P complete, then you do get Morava theory. And so you can see that P completion is the same as K1 localization for E1 local things. Right. And so the solution that I want to propose is to view everything as sheaves on a particular site. So this is going to be the proetale classifying site of this group G. And just as a warning, I guess I've already started doing it here. I'll sometimes drop the index H, so just H is going to be fixed. If it's missing, then it should probably be there. So this site, its object profinite GH sets, maybe up to some cardinality bound. And the coverings are kind of families which refine to finite and surjective families. And this site was studied by Batt and Schulze, and they showed that for a profinite group G, if you look at abelian sheaves on this site, that's a much better behaved analog of just the plain category of the topological G modules. So that's kind of topological spaces with a continuous G action. So in particular, this abelian category, I've given it away. This category here, it's abelian, and it has compact projective generators. And this means that it kind of really behaves very nicely. And there's an adjunction that relates, I guess there's a typo there, it should be this topological module category to this category of abelian sheets. And that adjunction is actually, well, the right adjoint is actually fully faithful if you restrict to those G modules that are compactly generated, which is some kind of point set topological condition, which is quite permissive. Okay, and they also show, so you might care about cohomology, and for topological modules, you can always define something that you call continuous cohomology using a complex of continuous cochains. But that won't necessarily be a derived functor if you're starting in this category. And on the other hand, you can look at your proetale site, and there, well, that's an abelian category with compact projective generators, so you can define cohomology. And there's a natural transformation relating these two functors. And actually, it's an isomorphism for if you look at modules that are discrete, which I mean is not super surprising because discrete modules already form an abelian category. So what's more interesting is that it's also an isomorphism for example, limits of towers of finite sets, finite G sets. And generally for a big class of topological modules. And just as a pointer, so when you look at the trivial group, even if you look at the trivial group, you get something interesting from this construction. You get the category of condensed abelian groups. Right, and so the way I want to formulate this equivalence is by saying that there's a sheaf of connective spectra on this proetale classifying site. And it has the following properties. So if we take global sections, then global sections you should think of as taking. So, okay, let me point out, so in the same way that we said, this is some model for topological G modules. And in general, if we take the infinity category of sheaves on this PG proetale valued in some infinity category C, which is nice enough, then we should think of that as object in C equipped with a continuous G action. So in terms of this dictionary, taking global sections corresponds to fixed points. And so what we get here is that the global sections That's the Picard spectrum of the KH local category. And on the other hand, because we've allowed ourselves all profinite G sets, we can evaluate on kind of a G torsa. And when we do that, then we recover the Picard spectrum of Morava E theory. Taken together, this is kind of saying this is this sort of statement. And furthermore, you can look at this sheaf of connective spectra, and it's going to have some homotopy sheaves, just using a standard kind of T structure. And they're valued in this category of abelian sheaf on PP Proet. And it turns out that these homotopy sheaves, you can go away and compute they're exactly the image of the homotopy groups of the Picard spectrum of Morava E theory equipped with a profinite topology. Okay, and so as a corollary, if you combine this with the properties that I gave you on the previous page for this proetale site, you get a descent spectral sequence for this sheaf pick E. And moreover, its E2 page starts with continuous group cohomology of G valued in the homotopy groups of pick E. And it converges to the homotopy groups of pick of the KH local category. So this corollary actually doesn't really mention at all any kind of condensed anything. Okay, and because, so this turns out to be quite a robust setting and quite a good model for continuous G actions. And some features that you can deduce are, for example, that you have a comparison of differentials with the Adams spectrum. So let me remind you, the Adams spectral sequence that I'm talking about has E2 page being continuous cohomology just of the homotopy groups of E. And when T is at least, I guess, 1, these agree with the groups in the E2 page here up to a shift. So let me write that. So phi T of E is phi T of A. So we can compare these differentials, which are in the descent spectral sequence on the previous page or on the Adams spectral sequence. And it turns out that the Adams spectral sequence also can be deduced from this formalism, and that allows you to compare differentials. So what we see is that if we look at groups that are insufficiently high T, then the differentials just match up. And the range for which they match up depends on which differential you're looking at. So we'll see some pictures later. And there's also a formula for the boundary of this range. So if we've got a class in ETTT, so this is something that's trying to converge to pi 0 of this Picard group we're interested in. Then there's a correction term. So we take this Adams spectral sequence differential, and then in the Adams spectral sequence, we add on, we use the ring structure, and we add on squared. Okay, and let me mention that you can compare results by Matthew and Vesna-Sternowska for finite group actions. Okay, so that's one nice feature, that we can compare differentials. And another thing you can say is there's a map that's kind of been studied a lot, which goes between this Picard group of KH local spectra and an algebraic analog of it, which is called PIC-H-alg very creatively. And by definition, this is the Picard group of this category of Morava modules. So again, there's a GH twisted, GH semilinear pi-star EH module. And it turns out that you can recover this map by truncating the spectral sequence to filtration at most 1. So if you truncate to filtration at most 1, what you'll compute is PIC-H-alg, and the map of spectral sequences will induce this map. And moreover, you can look at the -1 stem, and analogous to something proven by, I guess, Gepner and Lawson, this -1 stem computes what's the relative Brauer group. So this is the kernel of the map from the Brauer group of the KH local category to the Brauer group of the EA. Yeah, I really don't know where to put this little square, unfortunately. Hopefully we can live with that. Right, and so, yeah, as I said, but in order to prove these properties, you need to deduce also that you can construct the atom spectral sequence using this formalism. And the way to do that is to construct another sheaf, which maybe you want to do before proving the first theorem, called E. So this is now a sheaf of commutative ring spectra, which are KH local. And it has the following properties. So on global sections, we recover the KH local sphere. And when we evaluate on a torsa, we get Morava E theory. So again, this is making sense of the statement that the fixed points of EH the sphere. And again, on homotopy groups, we recover the homotopy groups of E with their profinite topology. So I'll give a sketch of this theorem. I don't think I have time to talk about the other theorem because I want to show you some pictures. So I'll focus on this. So one way to see this is that basically Devenat and Hopkins construct a sheaf, which I'll call E upper delta, which is defined on finite GH sets and surjections. And it goes into KH local infinity rings. And the key to extending this from, right, and we're going to use the fact that there's, an obvious inclusion called nu of the finite GH sets into the profinite ones. And this is actually a map of sites. So we're just going to try and extend in a stupid way along this. And the issue is that, I guess in general, if you can't extend a sheaf, then it won't necessarily, a sheaf that's defined, say, over here, then it won't be a sheaf on here. So that does work for sheaves of sets, but not sheaves valued in an infinity category. And the key point is this fact, which comes from the proof of the smash product theorem, which I guess I should attribute. That this extension from the sphere to Morava E theory is descendable. So that is to say that this is a Galois extension, and so you can recover the sphere as the totalization of this Kobar complex, but something much stronger happens. So actually, it turns out there's a splitting of this map into a finite totalization. And so actually this limit, which a priori is very infinite over here, looks a lot more like a finite limit. And that's the thing that lets you commute it with filtered colimits. And so once you know this for this extension from the sphere to EH, you know it for all of the intermediate extensions that Devenats and Hopkins construct. And actually this holds with the uniform index. And so when I left can't extend E delta to this bigger site, then it actually will already be a hyper sheet. Okay, and that's not quite the thing I want, because as I said, Morava E theory. So if I did this, then what I would get on a torser is the filtered colimit of the of E delta on some contracting sequence of open subgroups. And that won't give me Morava E theory, but as I mentioned at height 1, if I KH localize this, then I do get the right thing. So in a sense, the topology on Morava E theory is discrete, the kind of condensed topology up to KH localizing. And when you do this, the reason to do this is that then you can compute that the homotopy sheets are exactly kind of continuous maps, GH maps, into the homotopy groups of EH, which is this thing Y. Okay. Right. So this proves that there's some sheaf E and that it has the properties that you want to recover the atom spectrals. So I guess, yeah, maybe I can pause for a second if there's any questions at this point. And then I'm going to move on to computations. Right, so I'll continue. So let's have a look at what happens at height 1. So at height 1, as I said, the Morava stabilizer group is the p-adic units. And at the prime 2, the p-adic units split as C2 times Z2. And again, Morava E theory is just 2 completed K theory. So let's start with the atom spectral sequence at height 1. So you might compute this by first looking at the homotopy fixed point spectral sequence over here. So here we're looking at the C2 Galois extension from completed KO to completed KU. And this is a spectral sequence that's quite straightforward. So what you need to know in order to compute these differentials that I've drawn in is that in the homotopy groups of spheres, e to the 4 is 0. And so this class sitting up here has the answer vibe. And then by thinking about ring structure, you can deduce all of these red differentials. Okay, so that one's quite well known. And then you use that to deduce the form of the atom spectral sequence. Right, so this is the descent spectral sequence for this profinite Galois extension from KU2 to the K1 local sphere. But really, most of the cohomology of this group G1 is coming from Z2, and Z2 just has cohomological dimension 1, at least for two Pro2 things. And so we kind of see two copies. So in this picture, we see two copies of this picture that are kind of shifted slightly from one another. So again, this is kind of known and was known back in maybe the 80s in some interpretation. Okay, but we're going to use this to compute Picard groups. So now let's look at the related spectral sequence where rather than just look at the Galois extension, we look at what happens when we take Pic. So here we've got the Picard spectrum of the K1 local sphere, which we're recovering as the fixed points for the Z2 cross action on the Picard spectrum of KU. And now you can see this range where the differentials agree. So the range, wow, I got rid of it. So the range where the differentials agree is exactly, well, okay, so let me say the differentials here are all D3 differentials. And the range where the differentials agree is everything to the left, like, yes, everything that has a source in this region. So over there, we know all the differentials, and in particular, we know that everything will get killed, either be a target of a differential or the source of a differential on the E3 page. And then on the boundary of this region, we have this differential that I've highlighted in blue. And if we're interested in the Picard group, then that's what's computed by this column. Over here. So I had it written on the previous page, but again, this is S and this is B minus S. So each column is converging to some homotopy group of this guy. Right, so we want to compute this differential over here. And we had this formula for the differential on the boundary, in the boundary region in terms of the Adams differential. So this is this class Z. I'll go back so you can have a look at the Adams spectral sequence. So we're talking about this class over here, which supports a differential in the Adams spectral sequence. And also in the Adams spectral sequence, you can see that, I mean, the target of this differential is exactly where Z squared is living, regardless of whether Z squared is 0 or not. It lives in that. And so we can use that if we know that D3 of Z in the Adams spectral sequence is non-zero, then we know that D3 of Z in this Picard spectral sequence is going to be 1 plus lambda, where Z squared is lambda times D3. Lambda is in 0, 1. And so what you need to compute, the one bit of ring structure in the Adams spectral sequence you have to compute is that Z squared is not 0. And as a result, we get that D3Z is 2 times D3 in the Adams spectral sequence Z, which is 0, because it's landing in a D mod 2. Okay, so it turns out there's no differential. This differential over here doesn't exist in the Picard spectral sequence. And so this element survives. And so we can look at the subgroup of elements in the Picard group of K1 local spectra which are detected in filtration bigger than 1. So that's the kernel of this map to the algebraic gadget. And sometimes people use the notation symbol kappa 1 for that group. And so what we've shown is that kappa 1 is C mod 2. And that's something that Hopkins, Mahold, and Sadowski computed in a very different way in the 90s. Okay. Any questions about this computation? So let's talk about something that wasn't computed in the 90s. So for a start, I looked at a case height 1 and the prime 2. And the reason I did that is because generally things get easier at the fixed height when you make the prime bigger. So for example, at height 1, if P is an odd prime, then the cohomological dimension of ZP cross for pro P coefficients is 1, and so you'll have a vanishing line in the Picard spectral sequence already on the E2 page. And so kappa 1 is 0. Kappa 1 again being this kernel, this group of exotic Picard elements, ones that don't exist in the algebraic world. And actually, you can say something similar at arbitrary height. So if you have a fixed height, and then for big enough primes, the cohomological dimension of GH will again be finite. And the upshot of that is that if 2p minus 1 is bigger than h squared, then you have a vanishing line on the E2 page of this Picard spectral sequence, or its analog at height h. And that vanishing line will imply that there's just nothing that could live in this exotic Picard group for cohomological dimension reasons. So this recovers something that was proven separately by Sadowski and by Drew. Okay, so now let's look at Brauer group computation. So we want to compute the Brauer group of K1 local spectra relative to E1 relative to E2. So again, I told you this group is computed by what's in the -1 stem of this Picard spectral. We're looking at this column here. And Geffner and Lawson used these techniques for finite Galois extensions to compute relative Brauer groups. So they've thought about the extension from KO to KU, and they showed that the Brauer group of KO relative to KU is C mod 2. So how did they do this? They looked exactly at this spectral sequence for recovering pick of KO as the fixed points of the C2 fixed point of pick of KU. And this spectral sequence, you can kind of understand what it looks like. So, for example, when we look in high degrees in this region, all the differentials are copied over from the atom spectral sequence. And actually, Matthew and Sonoska proved that this differential, which exists in the atom spectral sequence, doesn't exist in this Picard spectral sequence. And they computed it. They did that exactly in the way we did on the previous slide, using this explicit formula. And as a result, you end up with this Z mod 2 that's left up here in the -1 stem. Okay, but now if we look at the -1 stem in this spectral sequence, when we go all the way down to the sphere, then there's a whole bunch of things. So, I mean, if we compare these spectral sequences, then we can transfer some of the differentials. So Geppner and Lawson give us these differentials, and it turns out you can transfer them over here. But you still have 1, 2, 3, 4, 5 generators, and you still have possible differentials. So we know there's no differentials out of the zero stem because we've already computed this Picard group. So we've computed all the differentials out of the zero stem. But there could be differentials like this one, or like this one, or like this one. So what we deduce from this is that the Brauer group has size at most 32. And I'm going to write again, this is Brauer 0, 1. Brauer 0, 1. So the 1 is the height, and the 0 is because it's the group of things that are inverted once we pass the E theory. What I told you we can deduce is that the size of this group is at most 32. So 2 to the 5. Okay, so, and you could try to compute the differentials out of this -1 stem, but that turns out to be kind of tricky. I don't know, or at least I didn't know how to do it. So what you can instead do is look at some intermediate spectral sequences. So rather than take these fixed points all in one go, we're going to first take the C2 fixed points, and then we'll take C2 fixed points. Right, I guess what I wanted to write. So that's written BPIC. So when you take the fixed points of BPIC, you get something that kind of behaves like a relative Brauer space. I guess the bit that I highlighted is the relative Brauer of KO2. So that's what we're computing over here in the -1 stem of this spectral sequence. So this one looks very similar. So this is the spectral sequence for going from pic of KO2 to pic of KU2, which looks very similar to this Geppner-Lawson spectral sequence, which is just the uncompleted version of it. And the only difference is that this class here, so this is, I guess, the units in Z, and down here we have the units in Z2, so we have a few extra classes floating around. And it turns out that this spectral sequence is sufficiently sparse, nevertheless, that once you import Geppner and Lawson's differentials to these ones here, then nothing else can affect this -1 stem, and you have to compute that there's an extension. But once you do that, you get that the Picard group of KO2 is Z mod 8, and the Brauer group of KO2 relative to KU2 is Z mod 4. Right, so now we've taken this, so we've done this internal bit, so this is the C2 fixed points, which is kind of the infinite bits, in the sense that C2 has infinite cohomological dimension. And now we need to just get rid of this Z2, which has cohomological dimension 1. And so that spectral sequence looks a lot simpler. So, I mean, you can see it's got cohomological dimension 1, and so there's a vanishing line at height 1 on the E2 page. And so all you have to do is work out extension problems. there's no possible differentials. So again, this is so I'm writing R with a circle for Z mod 2 to the R, and this is K over KO2, which is Z mod A, and this one is, and it turns out it has a trivial Z2 action. And this is this relative Brauer group. Which is Z mod 4. And so you end up with just two groups here and a possible extension between them. And in particular, there's no possible differentials here, so you know that the Brauer group, the -1 stem, is going to have size 32. And in fact, you can show that there's no extension between these two groups. And so you get that this relative Brauer group is Z mod 4 times Z mod 8. Okay, and I'll stop there.
Thank you very much. Thank you, Itamar. And I don't know how long you have before you need to run.
I can stick around until like 58.
Okay. Let's see, is there any questions? You can either just speak up or write in the chat, and I can read it out loud if it is. Okay, I will stop the recording, maybe that will help. But yeah, thank you very much for the talk. It was really good.